Hello, everybody. It's Tyler and Michael Foz here. We are in room 601 doing our presentation.
All right, Tyler, take it away.
You have a beautiful room, and hopefully, the projectors will stay on for this.
Yes, of course. Hopefully.
um, we will be doing problem 419. I have this on a note card right here. The question says steam flowing at a steady rate enters a turbine at 400 C and 7 MPa. The exiting is 0.27 MPa, and the turbine is 85% efficient. They want to know what is the quality of the exiting stream and how much work is generated per kilogram of steam. So, in our work, we have our givens right here. We converted temperature to Kelvin in case we ended up needing it in Kelvin in the future. I don't believe we ended up needing it, but that's okay.
No, we did not.
Um, we went through and went to the pressure and temperature tables, and we found HI and SI for our temperature of 407 MPa. With these numbers, we were able to begin working with our problems. So we wanted to find the quality of our exiting stream. So we have the quality problem or equation right here, where SI is equal to SM, and that is the entropy of the mixture. X is our quality. SV is something we'll have to calculate. We don't have just yet. It's specific entropy of saturated vapor. And we have 1 minus X again, quality. And multiply that by SL, which is the specific entropy of a saturated liquid. So we are missing SV and SL, but these are both variables we're able to calculate via interpolation. So we go on to our tables in the back of our book, and we can find a two values for SL and two values for SV. Um, and using the data points that we have in this table, we can actually interpolate the exact value for 0.27 megapascals, whereas the only options we had were zero point 0.3 and zero point 0.2 megapascals. So with those, we were able to calculate SL being 1.6 or 1.636 and SV being 7.25 kilojoules per kilogram Kelvin. We were able to then use these numbers and plug them all back into the equation, giving us a reversible quality of our gas being x equals 0.893. Now currently this is reversible. So this is not our final answer. We want to find the irreversible with using our efficiency. So now I'll pass it over to Michael.
All right. So, like Tyler just said, that um, we found efficiency, the reversible efficiency. So, in order to uh, move on and try to find the irreversible efficiency, we need to use this equation right here. It's the same exact equation that we just used over there with entropy, but now this is with enthalpy, where it is HM or H out, reversible, equals to the efficiency that we just saw, I mean, that we just calculated, times the saturated vapor for enthalpy, plus 1 minus, again, the efficiency that we just solved for, times the saturated liquid for enthalpy. So to do so, once again, we need to interpolate for HV and HL, and again, we utilize the same data point that we used with the final pressure given, which was 0.275. You go to the back of the book, where we go to the saturated pressure chart, I mean the table, and we look for HL, and to interpolate we have to use the points, I mean the pressures from zero point 0.2 and zero point 0.3, and same goes for HV as well. And from there we get, for HL we get 547.2, and for HV we get 2720.32. So from there, like I said, we utilize this HM equation, and we're actually solving for HM here because again we have X. So we plug in all the points where we have quality, we have HV. Again, we have 1 minus quality, and we just solve for HL as well, and we get HM, or H out prime, H out reversible, is 2,487.72 kilojoules per kilogram. And so from here, we develop a energy balance equation where delta H, or the change in enthalpy, is equal to Q plus work shaft prime. Again, this is for reversible. Um, this is for the reversible part, and Q is equal to 0 here. So our equation would be delta H is equal to work shaft prime, and again, so delta H is H out minus H in, and H out and H in are both reversible. H in we found in the very beginning of the problem when we use the initial data points. And again, we just found H out prime, or in this case, it's HM. We plug those in and we get work shaft prime. And again, this is reversible. So in order to find, I'm sorry, so work shaft prime is equal to negative 671.48 kilojoules per kilogram. In order to find work shaft actual or irreversible, you would have to multiply the efficiency which was given, which was 0.85 or 85%, and you multiply that by the work shaft prime or the work shaft reversible, and we end up with negative 570.8 kilojoules per kilogram. And then from there, we draw up another energy balance equation. In this case, it's going to be the same one as we just had earlier, which was delta H equals to work shaft, but in this case, this is irreversible. And so um, this will allow us to find H out irreversible. Okay. So we write up the equation as HM minus H in equals to work shaft, and in this case, HM is irreversible. And we plug in our data points for H in and work shaft irreversible, and we end up with HM actual or H out actual to be 2,588.4. And to end it all off, we go back to the equation to the equality equation, H, and we use it for again irreversible now. So we say HM actual or irreversible is equal to X times HV plus 1 minus X times HL. We have all these data points. We just solved for HM actual, and we have HV and HL from interpolating earlier. And this will allow us to find the quality of irreversible quality, I'm sorry, which would be X equals to, or quality equals to 0.94. All right. So that is it. Thank
Yeah.
you guys.
Thank you guys
I
for
hope you guys
watching.
enjoyed. And yeah, have a good night.
Yeah, everyone have a good day.